So right now I want to discuss section 6.1, exponential and logarithmic functions. So suggested exercises 1, 7, 13, 19, 25, 31, 61, and 65. And surprisingly enough, the topics are going to be exponential. You ready for it? You ready for it? And logarithmic functions. So, not so surprising. I'm going to ask that you work through examples 3 and 5. So we're going to do a lot of examples in this section, and those examples from the book I think are going to be especially useful because there's just a bunch here. You notice that I've given you a bunch of homework. We're gonna just have to do a whole bunch of examples of this. So an exponential function at least for our purposes, is a positive number raised to a variable. So for example, 2 to the x. Okay, so that's an example of an exponential function. 2 is positive, and I'm raising it to the exponent x. So what do we know about exponential functions? Well, such functions are one-to-one, and therefore if they're one-to-one, they are invertible, and that's going to be where logarithmic functions come in. Such functions are one-to-one and have a horizontal asymptote at y equals 0. So this should kind of make sense, because if I have a positive number, and let's think about numbers that are bigger than 1 for a moment, and I raise it to bigger and bigger exponents, it should get bigger and bigger and bigger. Now if I raise it to smaller and smaller exponents, it should get smaller and smaller. Think about raising it to negative exponents is like taking 1 over a bigger and bigger number, and that gets closer and closer and closer to 0, but it never quite reaches 0. So let's sketch a couple of these. Let's do f of x equals 2 to the x. Let's do another example. G of x equals 1/2 to the x. Okay, so if f of x equals 2 to the x, well, at 1 here we've got 2. Whoopsie daisy. I think I'm gonna, I'll do this a little bit lower. At 0 we've got 1. At 1 here we've got 2, and then already at 2 we're way up here at 4. At -1, that's 1 over 2, which is 1/2. -2, we're at 1/4. -3, 1/8. What we've got is this thing that goes up really steeply after we pass that value, and it is approaching the line y equals 0, but never touches it. Now for f of x equals 1/2 to the x, we're going to see it's exactly the same thing here. This is 2 raised to the negative x. So this is just f of negative x, which, as we should recall, is a horizontal reflection. So it should be here, here, here. It should look like this, right? So if I've got a number that's bigger than 1, it's going to go up to the right and horizontal to the left. If I have a number that's smaller than 1, it's going to go up to the left and horizontal to the right. Okay, that's the basic idea, basic shapes of these things. All right, so now let's do a more hands-on example. Solve for x. Let's do 3 to the 2x minus 3 equals 27 to the x plus 1. Now here I'm gonna give you a technique that will solve these problems, and then we'll later see a more general technique that will solve these problems. And that's nice. Sometimes you really might need to solve a problem like this. That's part of why I'm showing this to you. The other reason why I'm showing this to you is because if you can solve these problems and use these techniques, then then you're using some other facts about exponential functions that I'm wanting to get across to you. So in particular, so solution, let's start by writing our equation down again. 3 to the 2x minus 3 equals 27 to the x plus 1. I want to write these both sides as the same base. Now, when we have an exponent, here's the base, and when we have an exponential function, this is the base and this is the exponent, right? So here, I want these to have the same base. Well, there's 3 and there's 27. Somehow 3 is related to 27. And when I see 27, just because I'm so trained in multiplication tables, I think 9 times 3. All right, that's what I think. And I'm like, well, that's related to 3 somehow because there's a 9 there, so maybe I could divide by 9. But don't forget that 9 is 3 squared. So 27, more than being just 3 times 9, is also 3 cubed. So I can really write this as 3 cubed raised to the power x plus 1. All right. Now, how do exponents of exponents work? Well, if I have something raised to a power and then raised to another power, I multiply those exponents. So this is actually 3 to the 3 times the quantity x plus 1. Okay, so that's going to be 3 times the quantity x plus 1, which is 3 to the 3x plus 3. Now, these functions, the exponential functions in general, I told you are 1-to-1, which means they are invertible. But without defining the inverse, I can say, well, if I have 3 to the one thing equals 3 to the other thing, since these are 1-to-1 functions, that means the inputs had to be the same, right? What's 1-to-1? 1-to-1 says that if f of a equals f of b, that means a had to equal b. This is the definition of 1-to-1, right? So if 3 to the this equals 3 to the that, then this had to equal that all along. So what that means is because 3 to the x is 1-to-1, that means that 2x minus 3 is equal to 3x plus 3. So I subtract 3 from both sides and subtract 2x from both sides, and I get what? I get that x equals, negative 6. And that's my final answer. And we should, just take a second and check. Does x equals minus 6 make this true? So if I plug a minus 6 in here, what do I get? Well, I get 3 to the negative 15. If I plug a minus 6 in here, what do I get? I get 27 to the negative 5. But 27 is 3 cubed, so that's again 3 to the negative 15. So this is a reasonable thing to believe. All right, the last thing I want to do in this video is going to be a little bit more involved. So I think I'll take a new page. So find an exponential function. This is going to be a modified exponential function of the form. So I'm going to give you the form of this function. F of x equals b times a to the negative x plus c. So I'm telling you, an exponential function is of the form, something raised to a power, something raised to a variable power. Well, now we've just modified it. What have we done? We've horizontally flipped it. We've got a vertical dilation and a vertical shift, right? So the function of this form with a horizontal asymptote at, it's an at sign, it's a pretty bad at sign, at y equals negative 12, a y-intercept at negative 6, and an x-intercept at negative 1. Oops. Okay, so what we're going to need to do is consider how we can use all these pieces of information. Well, it's written with A, B, and C, so you might think, oh, well, let's just find A first, and then we'll find everything else later. But actually, I think what's going to be easiest is for us to start with this piece of information because this will directly lead us to C. And why is that? Well, an exponential function normally has a horizontal asymptote at y equals 0. So if this was of the form f of x equals a to the x, then the horizontal asymptote would be at y equals 0. However, it's not. Now, if I flipped the function horizontally, that's not going to change the horizontal asymptote. So the minus sign does nothing. If I change the value of a, that's also not going to do anything to our horizontal asymptote. Similarly, multiplying it by b might change the shape of the graph a little bit, or just by dilating it and pull it further away from the line, the x-axis, but it's not going to change the horizontal asymptote. So really, this is the key factor in determining the horizontal asymptote. So the horizontal asymptote of an exponential function is normally at y equals 0. But this has been shifted down by 12, so c equals negative 12, okay? And that's going to be our first sort of piece of information, is that c equals negative 12 because we've got the horizontal asymptote shifted down by 12. So now, I'm just going to kind of lightly cross that out because I've used that piece of information. So now, I'm going to use the next piece of information. So if I know something about the horizontal asymptote of my graph, now is that going to tell me about the x-intercept or the y-intercept? Just think about it for a moment. So I know when I plug 0 in for x, that a to the x goes to 1, and I'm left with b, right? So that would, if I plug 0 in for x, that would give me this factor, and this factor would give me b and c. But since I know c, that would essentially isolate b. So now I plug in x equals 0 and get f of 0 equals, well, let me slide this over a little bit. F of 0 equals, well, on the one hand, f of 0 is the y-intercept, and the y-intercept was given to us. The y-intercept is negative 6, right? So f of 0 should equal negative 6, but it should also equal this thing with 0 plugged in for x. So b times a to the negative 0, well, that's just going to be 1, minus 12, which means this equation simplifies to negative 6 equals b minus 12. Now, if I add 12 to both sides, that tells me b equals 6. So I've got b equals 6, c equals negative 12, and I've used this information. So now I need to somehow plug in an x-intercept of negative 1. Okay, what is an x-intercept of negative 1? That's a 0. That's a place where the function equals 0. That's what an x-intercept is. It's a root. It's a place where the graph of the function touches the x-axis. So let's use this piece of information. So right now, I know b and I know c, and all I need to find is a to completely describe my function. So I don't know, like when I just look at a function, I don't necessarily know where the roots are, but since this was given to me here, I have that, by definition of x-intercept, I have that 0 equals f of, well, what was that x-intercept? It's f of negative 1. And now I can plug that into my function, 6 times a raised to the power negative, and then I plug in my x value, which is negative 1, negative 1, minus 12, so there's my c. I simplify the right-hand side now, and I've got, well, a to the negative 1, that's a to the 1, so I get 6a minus 12. Well, goodness, 6a minus 12 equals 0, that's pretty easy to solve. I add 12 to both sides. I get 12 equals 6a, which tells me that a equals 2. Now I have a, b, and c. That gives me every piece of my function, so my final answer is f of x equals 6 times 2 to the minus x minus 12, and that's my final answer. Now, if we wanted to sketch this, not that the problem asks for this, but I'll go on ahead and do it anyway. One way to sketch this would be to start with 2 to the x. So we know it's going to be 1 at 0 and 2 at 1, and we just have a steep line up. sort of cranks over, and this is 2 to the x. Then if I horizontally flip it with this minus sign here, I've got 2 to the minus x, so it's going to be the same sort of shape, but now flipped. This is 2 to the minus x. Now let's multiply it by 6. Well, multiplying it by 6 just makes it steeper. And now this crosses at 6 instead of at 1. This has been crossing at 1. So it looks like this. This is 6 times 2 to the minus x. And just notice, 6 times 2 to the minus x, that's not the same as 12 to the minus x. The 6 is not being raised to the minus x power. Only the 2 is. Okay, so just to have that in mind. Don't try to simplify things incorrectly. Now let's subtract 12. So that's a vertical shift down by 12. So now instead of crossing at positive 6, it's going to cross at positive 6 minus 12, or negative 6. And we have the same type of shape with this being negative 12. Well, I guess I could move that a little bit. Well, that kind of got a little out of hand. Whatever. Negative 6 could maybe be right here. So I've still got this horizontal asymptote, and I've got this steep thing, and this would be my final function. F of x equals 6 times 2 to the minus x minus 12. You can see the horizontal asymptote down here at minus 12. See the y-intercept is indeed at negative 6. The x-intercept should be right here at negative 1. I guess that's that last piece of information. We can check that by plugging in a negative 1 here, and for this negative x, we get 6 times 2 to the 1 is going to be 12, and 12 minus 12 is indeed 0. So that's going to, I know the picture's not perfect, but that's what we're going to get. So you should probably review this process here, because this is a little bit involved. And even though there's a lot more in this section, I kind of want to break this section up into 2 pieces. So this is really going to be, video number 1, focusing on exponential functions. And then we'll do sort of another video on focusing more on the logarithmic side of